Hello everyone. In the previous two videos we have seen problems on nuclear decay and problems based on the principles of nuclear accelerators and detectors. Now we look into some other kinds of problems that can be possibly asked in your examination. So I've just titled them as miscellaneous problems so that it includes pretty much a problem of each variety. So let's look into the problems. So this is a problem based on determination of Q value of a nuclear reaction. So please remember, if you can recollect what we have done in the classes, usually we used to write a nuclear reaction like this. So you have a target nucleus and you have a projectile that is being hit on the target nucleus, which gives rise to some daughter nucleus and an ejectile or another atom or alpha particle or a beta particle or gamma radiations being ejected out or emitted out. So typically this is one way to write the nuclear reaction. The other way to write the nuclear reaction is like this. You write the target nucleus and inside the bracket you mention which is the projectile, comma, the ejectile, and after the bracket you write the daughter nucleus. So this is also a way to depict any nuclear reaction. So in your examination you could be given a nuclear reaction like this or like this. For example, if you take the example given here only, it is the target nucleus is nitrogen. It is being bombarded with an alpha particle or helium nucleus, and this gives rise to oxygen plus a proton. So this particular equation is given as N alpha comma P into oxygen. So please remember that this is one of the way to represent a nuclear reaction. So if you were asked the same in the examination, there is no need to get confused. So let us look at the problem given here. The problem says calculate the Q value of a reaction where the nitrogen 14 is bombarded with helium or 2He4, gives rise to 8 oxygen 17 plus a proton, and they have also given the mass of individual particles here. So let me just write down that. So the nuclear reaction would be something like this: 4 nitrogen 14 plus 2 He4 gives oxygen, which is 8 17, plus proton plus some energy in terms of Q, which is what we have to determine, and you have been given with the mass of nitrogen, which is 14 point, mass of neutron 14.00753, mass of helium 2He4 is given as some 4.00385, then mass of oxygen 17 is given as 17.0045, and mass of the proton, which I can directly write as MP, is given as 1.00813. And also please note here I have given in terms of AMU. or it can also be given as simply u. So they both mean the same. You don't have to get confused between AMU and u. So looking at this expression, you can understand that the q value can be determined as follows. So q value will be the mass of nitrogen 17 plus mass of helium minus the mass of oxygen 17 plus mass of the proton. Okay, and this we want the energy in terms of electron volts, which is the convention. So we just multiply it with into 931.5 or 931.11 or 931 MeV. Okay, so this is a very, very simple kind of problem. All that you have to do is plug in these values and then determine the q value. So this would be 14.00753 plus 4.00386 minus 17.0045 minus 1.00813 into 931.5. So solving this, we would get q as some minus 1.15 MeV. 155 MeV. So this is the value of the energy that is being used in this process where you bombard the nitrogen atom with alpha particle to give oxygen atom and proton. Let's look at another kind of problem. The problem goes something like this. The threshold energy of a reaction given here is found to be about 3.016 MeV. Find the q value of the reaction given the mass of the particles. So what is threshold energy? Is the energy that is required, minimum energy that is required for any nuclear reaction to take place. Okay, so let's first write the given nuclear reaction. So it says 5B10 is bombarded with a projectile. Okay, that's why it's a capital P. Gives rise to carbon C11 plus a neutron. Okay, so this is the nuclear reaction that has been given. What have we been given with? We have been given with threshold energy, so I can write it as some ETH. It is given as 3.016 MeV, and we have been given with the mass of the target and the projectile nucleus. So let me write that. So the mass of B is given as 10.00129. Sorry, it's not 10.0129939, and the mass of the projectile, which is capital P, is given as 1.007825. Okay, so we know that the expression for the threshold energy is given as ETH is equal to minus of Q value into mass of the target nucleus plus mass of the projectile divided by the mass of the target nucleus. So hence they have only given you with two parameters, so it is simple. You need to determine the Q value. So Q value simply will be equal to ETH into MT by MT plus P. Sorry, MT plus MP. Substituting these values, so you have 3.016 into 10.0012939 divided by 10.01239 plus 1.0078. So hence you can determine Q value as about 2.75 or 74 MeV. So you can be given with either of these terms and asked you to determine the other terms. So this is another way to determine the Q value using the threshold energy, or if they've given you a specific reaction, for example, let us assume they have just given you this particular reaction and they have asked you to determine the threshold energy, then all that you have to do is determine Q value as we did in the previous problem, and then substitute the Q value in this expression, this particular expression, to get the threshold energy of that particular nuclear reactions. Let us now look at another kind of problem. The problem goes like this: calculate the energy required to remove the least tightly bound neutron from the calcium 40 nucleus, given the mass of calcium 40 nucleus is some 39.9625 something. Mass of calcium 39 is 38.970 something, and mass of the neutron is 1.0866 something. So the logic here is this: so if you take the nucleus, say this is the nucleus, you know that there are protons and there are neutrons which are bound inside the nucleus. So you want to kick off one of the neutrons that is loosely bound or least tightly bound inside the calcium 40 nucleus. So calcium 40 nucleus. So if you kick out that, you would get calcium 39 nucleus plus a neutron. So you need to supply some energy for this process. So you are asked to determine this energy that is required to kick off. So given to us, so we have been given with calcium 40 nucleus. So we have mass of calcium 40, which is given as some 39.962589. We have been given with mass of calcium 39, so which is about 38.970691. We have been given with mass of neutron, which is 1.008665. Fine. So you know that the binding energy expression is given like this. So the binding energy of the nucleus is defined as A minus 1 plus mass of the neutron minus mass of the parent nucleus. So this is mass of the daughter nucleus plus mass of the neutron will be equal to mass of minus the mass of the daughter nucleus will give you the binding energy. So you know these values. This is, so if I have to write it, then it is mass of calcium 39 plus mass of the neutron minus mass of calcium 40. So that is what you got to do. Let us substitute these values and see what we will get. This is 38.970691 plus 1.0086665 minus 39.96258.9 into 931.5, just because you want it in terms of MeV. Okay, so just simple calculation will give you the answer to be binding energy is given as some 15.62 MeV. So if you have a calcium 40 nucleus, calcium 40, and you supply it with about 15.62 MeV of energy, then you will be able to kick out the least bound neutron and you will be able to get calcium 39 plus a neutron. So this is another kind of problem based on the binding energy of the nucleus. The next problem is something like this: which nucleus has a radius equal to half to that of uranium-235? This is a problem based on the radius of the nucleus. So what has been given to you is the atomic mass or mass number of uranium-235, which is 235. Simple. So you know the radius is given by R naught into a power 1 by 3. Okay, this is the expression for the radius of the uranium nucleus, where R naught is the Bohr's radius. So this can be, I'll keep it as R naught for sake of simplicity, and this would be 235 power 1 over 3. So this would be about R naught into 6.171. Okay, now what has been told? It's been told that the radius of the nucleus is half that of uranium. So if I take R dash as the radius of the new nucleus, this is Ru divided by 2. So you have to find out which is that nucleus. So let us see. So this will be R naught again into a dash power 1 over 3 is equal to R naught by 2 into 6.171. So you can cancel out R0 and R0. That is the reason I did not substitute for R0 in the previous steps. So you have A is equal to 6.171 by 2 the whole cube. This is about 29.37. So now we have to figure out which nucleus has about this mass number. So that is actually aluminium. Aluminium has 1329. So if you take the nucleus of the aluminium, then it is almost the half of the, I should say, radius, half of the radius of uranium 235. So this is a problem based on atomic sizes, nuclear sizes, and how you can determine how the radius of the nucleus is determined using the mass number or atomic mass. And this could be a kind of problem that could be asked in your exams. This is more of a generic kind of a problem. This has actually got nothing to do with nuclear physics alone, except for the matter that a positron is observed when there is a nuclear decay process happening, but otherwise it is a very generic kind of a problem based on energy expressions. So what has been given to you? An electron and a positron annihilate, or they react to give a gamma photon. Okay, so you need to determine the wavelength at which this gamma photon is coming out. So it is simple. You know, what is known to you is only mass of the electron or the positron is both the same, only their charges differ. That is 9.11 into 10 power minus 31 kilogram. Other than that, there is nothing known to you, and you need to know nothing actually. So you know E is equal to mc square. This is also equal to h nu, which can be written as hc by lambda. Fine. So all that I have to do is cross multiply this. So lambda will be equal to, I can cancel out 1c and 1c here. So I'll have h by m into c. But here m is not simply m, it will be me, because you have a positron and an electron which have the same mass. So this is a reduced mass, so as to say, or the collective mass. So let us just plug in these values. You know h is equal to 6.626 into 10 power minus 34 divided by 2 into 9.11 into 10 power minus 31 into 3 into 10 power 8. So the wavelength lambda can be written as 1.2122 into 10 power minus 12 meters. So that is the wavelength of the gamma ray photon that is being emitted out when a electron and a positron annihilate. Some of the kinds of problems that can be asked, as I have mentioned in the previous videos as well, these are all just indicative problems that I've chosen and solved. Please go through them once again and spend some time solving them at least once, so that you will get acquainted with the formulae and how to go about solving the problem. And remembering these formula will be helpful for you in solving the problems asked in your examination. All the best. If you have any doubts, please do get back to me.